Hello everyone, welcome to Tactica Imperialis and to today's video. Today is going to be another of my Tactica Tutorialis science lesson videos, and we're going to be doing today a GCSE science and physics topic, radioactive decay. In a recent lesson we had a look at the properties of radiation, which you can find linked in the playlist in the description below. And in that lesson we explored the three main types of radiation for GCSE, alpha, beta and gamma, in terms of what they were made of and how they interacted with other materials. Today's lesson is going to be a companion to that sort of brings the types of radiation into full view. We're going to look at the nuclei that they often come from in more detail and get into the mathematics of decay equations and decay chains. Our objective for today is to be able to complete decay equations for all types of radioactive decay. So that's our challenge for today. We've got plenty to do with it. However, if you are here looking for nuclear fission and fusion, which you might have done because of decay and fission, I'm afraid you won't find it here. Fission and fusion form a separate part of the radioactivity topic, and whilst I am very open to covering them in a lesson, if you would like me to do so, let me know, they are not part of this area for the sake of expediency and for the fact that they behave slightly differently compared to alpha, beta and gamma decay. As a result, they will not be here, I am afraid. But get now your writing equipment, pen and paper, laptop, whatever it happens to be, and make sure you have a calculator on hand. This is going to be a slightly more mathematical lesson compared to some of our others, and we also have to get our heads around atomic notation. So, without further ado, class is in session. Let's begin. So to get us started today, I want to review the three main types of radiation that we met in our previous radioactivity lesson. If you haven't watched that video, don't worry, it is linked in the description, but this should be a quick little catch-up for the basics of what you need to know for today. So, what I'd like you to do is I'd like you to do a quick little match-up between the types of radiation, the things that they're made of, so what forms that type of radiation, and also the source, where that radiation comes from, if you like. Now, you can answer this question in two ways. You've got options. So either you can write out the correct answers in rows. So you might say that that's right, and that's right. So I'm going to write a row of that answer, and that answer. And then the next row, you might say that one, that one, that one. So you write that one, that one, that one, and so on and so forth as one row. Or, as I'm going to go through in the solutions, you might do it like this. You might say that one, match up to that. And I said that one, didn't I? So matches up to that. And that one matches up to that and matches up to that. And so on and so forth. You've got two options for how you want to do it in terms of your answers. Whatever you think would make your notes look neater, especially after you've made corrections. So I leave you the choice. Give yourself about 2 or 3 minutes to do it, and when you've done that, click the link in the description which will take you to the solutions video for this exercise. Once you're happy and you've got your answers, we're ready to move on, and we're going to start by looking at atomic notation. So whilst we are getting into the mathematics of nuclear decay, we need to actually introduce some numbers so that we can do the requisite maths. We'll walk through the types of decay in a moment, but I want to introduce to you atomic notation, or as I have a habit of calling it, AZX, and I'll explain why that is in a moment. So on here you can see sort of this is a chemical symbol for uranium-235 actually. It's a chemical element, and this is sort of what you might see in some periodic tables, and it's definitely how you would write down the characteristics of an element from the periodic table into a decay equation. But what do these numbers actually mean? Well, there's two main numbers we need to focus on, and then this one in green I'll address at the end. So, this first one up here is 235. This number I'm going to call A. And we call that the atomic mass. Or, you might have also seen it called the mass number. You'll probably see both terms. Atomic mass is probably the correct term, but mass number comes up as well. So, what does that mean? Well, what that means is it's the total mass in atomic units of the nucleus or the atom. So it is actually equals to number of protons plus the number of neutrons. So, I should have done that. You take how many protons your element has, and you take how many neutrons the isotope of that element has, and you add them together, and that is equal to the mass number. Or more accurately, you're told what the mass number of something is, and then you work out the rest from there. This number here, 92, this number is called Z. I don't know why it's called Z. I don't. I'm guessing, I think it comes from the German, but I'm not fully up on all my linguistics and my history as to why it's called Z, but it is. And this is known as the atomic number. Or you may also have seen it called the proton number. Both terms are correct. Atomic number is the official term, just like atomic mass, but proton number is a very good explanation because it is equal to, you guessed it, the number of protons. And just the number of protons. So the mass number is protons plus neutrons. The atomic number is just the number of protons. And with those two numbers and the chemical symbol, you are fully equipped to do decay equations. This is the chemical symbol of the element that you are working with. And we're going to call that just X, because X is the standard sort of mathematical term for an unknown. So when we're talking about a generic nucleus where we don't know its chemical symbol, we'll write that as an X, and I'll show you what I mean in a moment. The last number that we need to draw attention to here is this one in green, this 143, which I think is correct. So this number you don't often see written down, hence why it's in green, but it can be useful for you to have it written down. So this one here is the neutron number. And it is equal to A take away Z. And we sometimes call it N, capital N. So if you know the mass number and the atomic number, you can work out the neutron number by subtracting this one from that one. As for how it's laid out, you always write it in this layout. So you have the atomic mass in the top left, the atomic number in the bottom left, next to the chemical symbol, which is full size. And the neutron number, if you write it, is at the bottom right. So the general AZX notation that you're going to get very used to throughout this lesson, I've just done you a full label there, so take that down if you want it, will look like this. For every single nucleus and piece of radiation we use, this is what it's going to look like. Because I wanted to show you that first as a full worked example. So get very used to the idea, this is why I call it what I do for atomic notation, of AZX. AZX notation is something you should get very, very used to using when it comes to decay equations, because you're expected, certainly I would expect, that you would be writing in this notation a lot. So just as a sample question, I'm just going to walk through it in here. Can you write for me oxygen 16, so the isotope oxygen 60, which is sort of normal isotope, in AZX notation? Just once you've got some notes down, can you have a go at writing down oxygen 16 in AZX, just to give yourself a little bit of practice? Give yourself 1 minute, pause the video. And you should get out, once you've had a go at that exercise, which you should have done by now. So 16. So 16, in this case, represents the mass number. We usually write the atomic mass of an isotope, because remember, or sort of a definition you might want to know. So this right here is the atomic mass, because isotopes, which is a term you've probably met before, have the same number of protons but a different number of neutrons. So writing down the atomic number would do nothing. It doesn't make a difference for the isotope what their atomic number is because it's all the same. The atomic mass allows us to tell the difference. So this is our atomic mass. So it would be 16. The chemical symbol for oxygen, most of us know, is O. And then we just need to work out the number of protons. And to do that, you'd probably go and look at the periodic table. Now, it's quite common, and certainly I usually hand out periodic tables to my classes, and you would probably have access to a periodic table somewhere, I think, or you'd be given the relevant data required to make it work. But if you had a chance to look it up on a periodic table, or you just know this one, you would know that the atomic number, which is also equal to the number of electrons, for oxygen is 8. Oxygen has an atomic number of 8, and so in AZX notation, it is 8, 16, and then a capital O for the symbol. So that's atomic notation. You're going to get very used to it very quickly, because I'm going to use it a lot. But now we're going to go over and talk about the various types of decay equations and the maths involved. Much like chemical reactions, there's a bit of logistics that goes into forming a decay equation. So these are the key notes that I think you would need to take down. So like a chemical reaction, decay equations have an arrow that connect what you start with, the initial product or components, to what you have at the end, the final products or components. So you start with the initial stuff on the left-hand side, and you draw an arrow connecting them to the final products on the right-hand side. For these equations we're going to do today, there will only be one nucleus on the left-hand side, and there will be 2 final products on the right-hand side. However, there is more complicated versions of that, and we will talk about decay chains at the end of the lesson, and there is also fission and fusion that we could discuss another time to slightly complexify this. When we're writing a decay equation down, each of the nuclei involved and the radiation involved are written down in symbols with AZX notation, with that full atomic notation we just discussed. So, as I'll write up in this top corner, remember how we wrote it? We had A, X, and there's Z. And we have all the meanings for those as normal, where we have the atomic mass, the atomic number, and the chemical symbol. So I've written down here the 4 types of radiation that can be used in decay equations. We've discussed alpha, beta, gamma at length, and you can go back to the starter solutions to check what they're made of. And we also have the neutron. Your little task, I'm going to give yourself about 2 minutes to discuss if you've got people around you, or to do this, is to try and write these in AZX notation. So think about what they're made of. Think about, do they have an atomic number? Do they have an atomic mass? And for beta radiation, I'm going to give you one little hint. In fact, I'm going to give you just this one for beta. Beta is treated as having an atomic number of -1 because even though it's not a proton, its charge is negative. So to make the equations balance up, we write it as having a -1. That's the only help I'm going to give you. So 2 minutes. Try and work out the atomic mass and the atomic number for each of these types of radiation. Good luck. Off you go. Okay, if you haven't already, pause the video to finish off, because obviously I know I didn't say pause the video there. So pause the video and finish off. And then when you're ready, let's go over the solutions. So, alpha radiation. If you check the starter, remember that we said that alpha radiation was made of 2 protons and 2 neutrons. So, just by knowing that information, we should be able to intuit it's AZX. So, if it's got 2 protons in it, then its proton number, or the atomic number, must be 2. And we also know that its proton number, being 2, its neutron number is also 2, because it's made of 2 neutrons. I'm going to write that there, which you can sometimes do. And if we add those 2 together, the proton number plus the neutron number makes the atomic mass, or the mass number. So the mass of an alpha particle is 4. And we talked about that actually in the properties of radiation lesson. We said that it has an atomic mass of 4. because it's made of 2 protons and 2 neutrons. Now beta, I gave you that its atomic number was -1. It's technically not a negative proton, it's an electron, but when you do equations involving this, the elements that come out will only come out correctly if this reads as a -1, and we'll talk about that in a moment. So what about the atomic mass of an electron? Well, it's not a proton and it's not a neutron. In fact, it doesn't contain either of those. And we talked about it in the previous video. Its atomic mass is 0, relatively speaking. It's not actual 0, but it's close enough to 0 that we can write it as 0. Now, gamma has no charge and no atomic mass. So its mass number is 0 because it has no mass whatsoever, and its proton number by extension must be 0. It also doesn't have a charge, so unlike beta where we write a -1 to reflect its negative charge, gamma doesn't even have that. Now as for the neutron has a neutron number of 1, but its proton number, because it's not a proton, it's a neutron, is 0. So we add those two together and we get 1. So in AZX notation, it is 1, 0 for the neutron. So those are the 4 types of radiation in AZX. I'm now going to model for you 2 decay equations, one using alpha and one using beta. After that, there's going to be a series of exercises that come up on screen, and you can have a go at answering some decay equations for yourselves before we move on to decay chains. So what we're going to do now is a couple of worked examples, just to give you an idea of how to write down decay equations based on the information that you're given. And I'll make sure you have the information in the required questions that I'm going to set in a moment. However, I would also find either, if you've got some in your notes or on the internet, a very simple periodic table, one that gives you atomic numbers and mass numbers for each nucleus, but you don't need ones that give it all to the decimal points. Find a nice simple periodic table that you can use as a reference point. So the first decay we're going to look at is the alpha decay of radon-219. So the isotope number 219 of radon with an atomic number of 86. Again, this information will be given in every single question. So first off, we need to write our initial nucleus in AZX. So let's do that. So our mass number, our A, is 219 because it's the mass number on the end of the isotope. The atomic number, we're told, is 86. And the chemical symbol for radon is Rn. I just know that, but you can check me in a periodic table if you don't believe me. And that's now going to undergo a decay. There are no further things on the left-hand side in the initial components. So that's going to end up as a new nucleus following the alpha decay. So we know we're going to end up giving off an alpha particle. So let's write that down. So we have an alpha particle, and in AZX, alpha is 4, 2. Now I've written it over here because typically you write the bit of radiation on the end, but you could write it here equally. I've written it there because this is just the convention. But now I need to work out what this mystery nucleus in the middle that I'm left with is going to be. And I do that actually doing some very simple subtraction. So my initial atomic number was 86. So I had 86 protons when I got started. My alpha particle has carried off 2 protons. So it is taking away 2 protons and 2 neutrons from this nucleus to leave behind the new nucleus. So the new nucleus must have an atomic number of 84. The atomic number on the right-hand side must add up to the atomic number on the left-hand side, because you can't just invent new protons and neutrons. And the same applies to the mass number. So if I had 219 protons and neutrons in total, and 4 of them were carried off as an alpha particle, then what's left over must be 215 protons and neutrons in total. And if I had the neutron number here, which would be 133, you could have the 2 there and 131 would be written there to make that add up to 215. You can have the neutron number if you want to check it, but I assure you it does add up. So that's all you do, is these 2 numbers, so add them up is equal to that number. So the total number of protons and neutrons you end up with must be the same as the total number of protons and neutrons that you start with. It's actually dead simple, even though it can be a little bit counterintuitive to look at the first time. Now we've got to work out what the chemical symbol is of our new nucleus, and this is where you need the periodic table. Now, I know, because I looked this up, that the element with atomic number 84 is polonium. And when you're looking for your reference for your nucleus, this is the number you want to be looking at. Because there are lots of isotopes that can change the neutron number. The atomic number is locked to the element. So only polonium has an atomic number of 84. That's why I can write polonium there. There are several nuclei that could have an atomic mass of 215. Look at the atomic number or the proton number as your priority. So that is an alpha decay equation. Now let's do one for beta. Just again to give you a bit more idea about how to go about doing it. Now, gamma's a little bit more awkward, but I'll give a bit more hints in the actual question about how you do that one. So, beta decay of, let's say, carbon-14. That's an iconic bit of radiation. Carbon-14, because we actually use this for carbon dating, if you didn't know, which is something that you do, I think, look at as part of the radioactivity topic. And carbon, you can look at your periodic table, has an atomic number of 6. Again, I know that off the top of my head. I've done this enough times, but you could always check that, and I'll make sure you're given it in the question. So, what is our initial nucleus? Well, it's got a mass number, an atomic mass of 14. It's got an atomic number of 6, and it's carbon, so its symbol is a capital C. And it's going to undergo a beta decay. So we'll write our beta particle down as our secondary product over here. And in AZX, remember, beta has an atomic number of -1, and its mass number, its atomic mass, is 0. And now we just do the same thing again. So, looking at the number of protons, I had 6 to start with, and I have a net -1 because a neutron has changed into a proton inside that nucleus of carbon in order to create this electron. That's where the -1 becomes so useful. A neutron has changed into a proton, so the nucleus has gained 1 proton. So to balance up the numbers, the beta is like having a negative for the atomic number because it's had to be created out of a new proton. So if I add them up, 6 add -1. No, that's wrong. 6 take away -1 because of the fact that this take away that's going to have to equal. Oh, sorry, these two have to add up to equal that, means that this number here is going to be 7. Because 7 add -1 equals 6. Sorry, I had a bit of a hash of explaining that. So because these two numbers have to add up to equal that, 7 add -1 equals 6, therefore that number must be 7. 14 and 0, well, this hasn't taken any protons and neutrons away, so the actual number of protons and neutrons doesn't change, and this adds up to how beta decay works. Remember, a neutron has changed into a proton, but the number of total protons and neutrons, so I had 6 and 8, now I have 7 and 7 because one of the neutrons became a proton. That still adds up to 14. So the mass number, the atomic mass, does not change. And I just need the symbol for this one. You can look it up in your periodic table. That would be nitrogen. And this is actually quite a common decay, beta minus decay for carbon-14 into nitrogen. It's used as part of carbon dating to look at carbon-14 levels. So that is how you go about decays. So coming up on screen is going to be one decay equation for each type. So you're going to get a sort of short word description as well as the name of the isotope you're using and the atomic number of that isotope. What I'd like you to do is what I've done here. Create the decay equation for each one. I will give you some additional hints on the sheet about gamma because it's slightly more complicated than it looks. In fact, I'll give you a lot of help with that one. So have a go at those. Give yourselves about no more than 10 minutes. I think probably 7 or 8 is appropriate, depending on how confident you feel and whether you need to watch this again. But when you've done that, the link to the solutions will be in the description as before, so you can click that link and we'll go over the answers there, and then you come back and we'll talk about decay chains, which is going to bring all of this together. Now, I don't normally mandate going to the solutions for all viewers because I know not everyone's following these as an exercise. However, in order to understand decay chains, you have to have this locked down. You have to understand this thoroughly as to what we're doing. To make that work, you're going to have to understand it. So do check the description for the solutions if this is not crystal clear, even if you're not going to attempt the exercises. Okay? Hopefully that's clear. Check the link in the description and then we'll talk about decay chains. Okay then, so now that we've got an idea of decay equations, the most complicated thing we can do with that as part of GCSE is decay chains, which is sort of taking decay equations and dragging them out a bit. So a decay chain essentially is a bunch of decay equations that go one after another. So this is like think about it like this. So one nucleus that is unstable is going to decay. But the nucleus it decays to is also unstable, so that needs to decay. And then that one is also unstable, so it needs to decay. And it happens several times until the nucleus finally reaches a stable nucleus that it can sit at without decaying. And we can track all of those decays in a decay chain. Now, the typical protocol, you can write them down in full as a series of decay equations one after another. So first decay equation, second decay equation, third decay equation, if you like. But you can do it faster, and to get it into one simple chain, we generally take the radiation type out of the equation. You can label them, and I'll do that in green with this worked example, but typically we don't actually write them in. So we don't write goes to something plus alpha, goes to something plus gamma, goes to something plus neutron. That's not the typical way we do it. So let me show you what I mean. So we have this example decay chain here, 216 polonium. So I've written that as a shorthand AZX notation. Polonium, you might remember, has a atomic number of 84 and is going to end up at lead 208. Now, lead, I've actually pulled out one of my periodic tables over here. So there's a periodic table if you're interested. I'm just going to find lead. There it is. 82 is its atomic number. So it's going to end up at lead 208. And I want to do that by doing an alpha decay, a beta decay, an alpha decay, and then a beta decay. So let's write down that chain. So we start off with 21684 polonium. And then what happens is an alpha decay, which I'm just going to label in green up here. So it's an alpha decay is happening. So I know, you might remember that alpha is alpha 42, so 4 atomic mass, 2 atomic number. So the atomic mass of my new thing is 216 take 4 is 212. And the atomic number of that is 84 take 2 is 82. And that is going to be 82, actually matches up there, lead 212. But we're not at lead 208 yet. We have to do a beta decay now. So, new decay. And this one, as I said, is going to be beta. Now, I'm writing these in green because you don't always have to write this. This is me being sort of extra thorough. So, beta was 0 minus 1, so 0 mass number minus 1 atomic number. So we have 212 still up at the top, but we add 1 up here because 82 take away minus 1 is 82 add 1, which is 83. Then we go back to the periodic table and we look for 83. It's up here. That is bismuth, Bi, just there, 83. 83 is Bi for bismuth. Then I'm told I have another alpha decay. And I'm going to end up going 4 off of that, so 208, and 2 off of that, 81. So 81 on the periodic table, let's have a look, is TL, or thallium. It's not T capital I, it's T lowercase l, which is thallium, it says. Yep, thallium. T lowercase l. And then finally, there's going to be one more beta decay. And that's going to end up at 208 not changing. Add 1 to this because of beta, so 81 take minus 1 is 82. And 82, as we said, is lead. And that is the full decay chain for 216 polonium to 208 lead, or polonium 216 to lead 208 is how we typically write it down, as you will have seen in the previous exercises. So that is a decay chain written out in full. That's all you'd be asked to write. Now, there's nothing to stop you writing down lead 212 plus alpha 42 goes to 2112 bismuth plus beta 0 minus 1. However, this is the shorthand. You wouldn't even need to write these little symbols for which decay is happening where, because you're told in the question quite often what decays are happening and in what order. So there's going to be another example of this that I'm going to put up on the screen for you, and you'll have a chance to work on that, and the solutions for it will be in the description. But that is how decay chains go. You have your initial nucleus, you're told where you're going to end up, and you're told how you're going to get there. All you then have to do is apply what we've done with decay equations over and over and over and over again, as many times as it tells you, until you end up in the right place. And it actually gives you a way to check your own answer, usually, by telling you where you're going to end up. Or it will ask you, it does this, 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 and this, what's it going to end up as? So the sort of final question, which is going to be what the one we're going to give you is going to be, such a thing is going to decay like this, 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 and this. Where's it going to end up? So that's going to be the question that's going to come up for you in a moment. But decay chains is about as complex as things get for decay equations at GCSE and nuclear decay in general. You won't need to go any further than this until you hit A level, and there's a lot more there to discuss. But I'll put that question up on the screen now. Give yourself about 3 to 5 minutes, certainly no more than 5 minutes, to work on it, plan your decay chain, get your periodic table and look through it, and work out what the final answer is going to be. The solution will be in the description, so it'll be the third of the 3 links in the description. And then once you're happy, you've checked your answer in there, we're going to wrap up the lesson in the next section. So, for our final little activity, a little summary of everything we've done today, I'm going to take advantage of our online format and use the comment section as a way of assessing what you've done. So obviously you've been assessing yourselves with the activities you've gone along with the solutions videos, but I want to see what you can do. So in the comments, I would like you to write an exam-style question on what we've done today. Decay equations, atomic notation, decay chains, whatever you'd like it to be. I'd like you to write a question that sort of fits with the questions I've asked today, or that you've seen on past papers or in exams in the past. Write those sorts of questions in the comments and label them with the word question. Now, the reason that we're doing this is partly so I can see what you've done and see if you've got it, and partly because it provides, in the comments section, a quiz for everyone watching this video, whether that's now or in 5 years' time. This is going to create basically a giant question pool for people to come along and check their understanding. However, I'm going to caveat that by the fact that this is the YouTube comment section. I've seen it enough times. I'm going to be moderating this comment section quite heavily. By that, I mean that only comments I approve are going to appear on the comment section of this video. I'm not doing that to censor people. I'm not doing that to shut anyone up. I'm merely doing it to make sure that the only questions that people can answer are actually questions that are useful, that are correct, and that follow up with what we want to do. If you put an incorrect question, so it doesn't work, then I'm more than happy to reply to you in a comment and explain why that doesn't work. And you can maybe take the comment down, edit it, whatever. But only the comments that are correct with their questions are going to get approved. All other comments I'm going to approve anyway. But just for the questions, I'm going to moderate them to make sure that anyone watching this video has got a useful set of resources. So don't worry, this is a one-off, just so that the questions are of a useful quality for everyone else who watches this video in future. Make sure as well to go back through the video, copy up any notes that you missed because you were listening to me talk. You can pause the video, write stuff down, add some annotations, check the solutions videos in the description to make sure that you've got everything in order, and then we'll be done. So, I do hope you enjoyed today's lesson. I hope that it was informative and gave a good view into radiation, paired up especially with our properties lesson that we did a couple of weeks ago. So this one and that one together should give you everything that you really need to know about the types of radiation and how they work. There is more to radiation, of course. Activity and half-life, the applications, particularly for medical physics, and there's nuclear fission and fusion that I'd happily do in a future lesson. But in terms of alpha, beta, and gamma, and the neutron, that's it. Those two lessons should be everything. Anyway, I hope you enjoyed it. Thank you very much for your time. And if you have any requests for a future lesson, do let me know in the comments. As I say, I will be reading them all for moderation, so let me know if there are any lessons that you'd like me to do, any topics you'd like me to cover, so that I can make sure this content is tailored to providing the most benefit for as many people as possible, rather than just being topics I pick off the top of my head. Because I love doing this, but doing it with you guys in mind is just as important. So let me know any requests as well as your questions for everybody else. But either way, class dismissed. This has been Tactica Imperialis, and this has been my lesson on nuclear decay. Thank you very much for watching. Bye for now.